Hi, I'm Eric Kai, the chemical statistician, and today I'm going to show you that under the Hardy-Weinberg equilibrium, the allele frequency of a trait for a population remains constant from generation to generation. That is a big mouthful, so let me illustrate or frame what I'm trying to do in the form of an example. Okay? So let's take the shape of peas as an example. This has two alleles, smooth and wrinkled. It turns out that the smooth allele is dominant and the wrinkled allele is recessive. Now, let theta be the allele frequency of the smooth allele. Okay? So we can express that as a probability. So P1 of the smooth allele is theta, and 1 refers to the first generation. Since there are only two alleles, wrinkled and smooth, the allele frequency of the wrinkled allele must be 1 minus theta. Okay? So what I'm trying to show is that if the allelic frequency of the smooth allele in the first generation is theta, then in the second generation, the allelic frequency of the smooth allele is also equal to theta. Okay? So remember that the Hardy-Weinberg law predicts that the allele frequencies of a trait for a population of interest remains constant from generation to generation, as long as its 7 assumptions are fulfilled. And I'll let you look on the internet or read a textbook about statistical genetics or genetics to learn what those seven assumptions are. There are 2 that are important for our tutorial today: the assumption of an infinitely large population and random mating. Okay, so to show what we're trying to show, which is that the allele frequencies stay constant from generation to generation, it's best if we start by looking at the possible genotypes and the genotypic frequencies in the second generation. Okay, so to do that, we need to look at the allele contributions from the father and the mother. Okay, now remember that we're looking at an infinitely large population. That's one of the assumptions of the Hardy-Weinberg law. If you're sampling potential parents from an infinitely large population, then you're really sampling with replacement. And if you're sampling with replacement, then the allele frequencies stay the same from one sample to the next. Okay? Because as soon as you are, if you're sampling with replacement, as soon as you take a sample out, you're also putting it back in. So the probabilities stay the same from draw to draw. Okay? So if I declare that the allele frequency for the smooth allele is theta for and I'm drawing from an infinitely large population, then I can be assured that both the father and the mother will have the same allelic frequencies, okay, for S and W. So that's why P1 of S is equal to theta for both the father and the mother, okay? And of course, P1 of W is equal to 1 minus theta for both parents. Now, let's take a look at the possible genotypes in the second generation. So if the father contributes to smooth allele and the mother contributes to smooth allele, then the genotype would be smooth and smooth, which I'll denote as simply S and S. Okay. If it's wrinkled from the father, smooth from the mother, then it's SW. Same case down here. If it's smooth from the dad, W from the mom, wrinkled from the mom, then it would be SW. Okay. So these 2 cells are the same. If both are wrinkled, then the genotype, of course, is WW. Okay. Now, let's figure out what the genotypic frequencies are. And this requires the other assumption that I alluded to earlier, random mating. Okay. So if they're randomly mating, if the 2 parents are randomly mating, then this joint probability of smooth and smooth is just the product of the marginal probabilities. Okay, that's the definition of independence. The joint probability is just the product of the marginal probabilities. So then this is just equal to theta times theta, or theta squared. Okay? P2 of SW is just theta times 1 minus theta is equal to theta times 1 minus theta. And same case down here. SW is equal to theta times 1 minus theta. Okay? P2 of WW is equal to 1 minus theta all squared. Okay, so we now have the genotypic frequencies for all of the possible genotypes. Okay? So now the question is, how can we use this information to determine the allelic frequency of the smooth allele in the second generation? And here's where I really don't like any textbook or any website that I have found about statistical genetics regarding this topic. Because every time I see this calculation made, I see the source jumping straight into this line. Okay? They say that the allelic frequency of the smooth allele in the second generation is equal to the genotypic frequency of SS plus 1/2 times the genotypic frequency of SW. But they never explain why that is true. Okay? It is true, and if you follow the math from that point on, you'll find that P2 of S is equal to theta. Okay? So that's the punchline down there. That's what we're trying to prove. And if you follow the math, if you follow the algebra, which I've done for you, you'll see that that is true. But where on earth did that line come from? No book or no website has ever explained that. Okay, so I had to figure that out, and this is where I'm trying to make things easier for you by explaining where that line comes from. Okay, so it's easier if we go back to the definition of an allele frequency. That is equal to the number of S alleles in the second generation divided by the number of all possible alleles in the second generation. Okay? Now, we have two genotypes that contain the S allele, the SS genotype and the SW genotype. Okay? So, let's break this apart into the SS genotype and the SW genotype. In the SS genotype, we have two S alleles per genotype, so it's 2 times the number of SS genotypes divided by 2 times the number of all possible genotypes. Okay? Okay, so I hope that's clear to you. There are 2 alleles in this genotype, so that's why I multiplied by 2. And each genotype has 2 possible alleles, so that's why I'm multiplying by 2. Now, let's take a look at the SW genotype. There's 1 S allele in an SW genotype, so I'm going to multiply the number of SW genotypes by 1 of SW genotypes divided by 2 times number of all possible genotypes. So notice that the denominator for both of these fractions are the same. So these 2's cancel. So this now just becomes the fraction, or the proportion of SS genotypes in the second generation, which of course is just the genotypic frequency, P2 of SS. Okay? And this, of course, we ignore the 1 and the 2. This, of course, is the proportion of the SW genotypes in the second generation. Okay? And that, of course, is P2 of SW, the genotypic frequency of SW. And I'm multiplying by 1/2 because the SW genotype only has one S allele. Okay? So that is where this line comes from. Now, in this table, we see the SW genotype twice. So that is why P2 of SW is equal to 2 times theta times 1 minus theta. Okay? P2 of SS is just equal to theta squared, as we see here. Okay? And if you follow the math, you'll see that P2 of S is equal to theta. And that is the result that we want. And we have now shown that under the Hardy-Weinberg equilibrium, the allele frequency of the smooth allele stays the same from the first generation to the second generation. Okay? So, I hope that was interesting to you. This is a lesson in statistical genetics. As always, you can visit my blog, The Chemical Statistician, to get your short lessons and in-depth tutorials about statistics, machine learning, chemistry, and math. And you can follow me on Twitter at ChemStatEric. Thank you for watching this video, and I hope that you learned something useful today.